So the first thing I want to talk about is the lab we did yesterday. So normally this would have been a lab that we would have done in person. In fact, I think you could tell this was done at Leiden, and it was done on one of those days when they were selling carnations. So those are someone's flowers. Um, we have these two carts, and you saw this yesterday. This one has a spring-loaded piston. When Mr. Hammond pushes on that button, the spring-loaded piston pushes the two carts apart. So I know their masses. Mr. Hammond put them on the screen, and at the very beginning, it's neither cart is moving. Can someone tell me what the momentum of the cart on the left is? All right, it's zero. That's right. And the card on the right also zero. So neither card is moving, so neither one can have momentum, right? Momentum is mass times velocity. So the momentum of cart one plus cart two at this point would be zero. All right. Now, Mr. Hammond then he comes in with the meter stick and he pops it, and the two carts push apart. All right. Now he goes in and he looks at the velocity. So at this point, you guys, can someone tell me either with your voice or on the group chat the the cart on the left? We'll call that number one. Doesn't really matter. So the cart on the left, what was the momentum after Mr. Hammond tapped it and the piston exploded? What was the mass times the velocity? Okay, Angel, I'm going to call on you. What was the mass times velocity for the cart on the left from yesterday's lab?
I wasn't here yesterday.
Okay, I'm sorry about that. All right then, Aldo, what was the momentum for the cart on the left? Aldo, are you there?
I'm looking for it.
Okay, all right. Did you find it, Aldo?
Momentum?
Yeah, what was the momentum? So you had the table, right? And the first
Yeah.
you had the mass of the first car, the velocity of the first car, and then you wrote the momentum down. So what was that? What's the momentum? It was in the third column of that table.
Um, 0.57.
Okay,
Uh,
0.57, and remember the units would be kilogram meters per
sure.
second.
Yeah.
And then Aldo, what was the momentum of the second cart?
0.46. No, 47.
0.47?
Yeah.
Okay. Okay. So and this cart, if you look at the video, we had the cart with the piston. The cart with the piston moved to the left, and the other cart moved to the right. All right? Now remember, momentum is mass times velocity. Is velocity a vector or a scalar? Caitlin, do you remember, is velocity a vector or a scalar? It's a vector, right? So direction is important with a vector. If we make one of these directions positive, then the other direction would be negative, right? So if, let's say, this cart is going in this direction, we'll call this positive momentum, and this card is going in the other direction. We'll call this negative momentum. Now, if we had done this lab perfect, you guys, these two momentums would have been exactly the same, just in opposite directions. So the starting momentum was 0. The ending momentum would be, if these were the same, it would be Brian, what do you think? What would the ending momentum be if those were the same? Brian?
Yes. What was the question? I didn't hear.
What would the total momentum of the system be if both of those carts had the same momentum?
If they have the same momentum,
Mm-hmm.
would it be 0?
It would be 0, right? Because one is going to end up being positive and one will be negative. So the total momentum was 0 before the two carts were released. And after the two carts are released, it's still 0, right? What you guys did yesterday without even knowing it is you were proving the law of conservation of momentum. So there was a question on there, how did the momentums compare before and after, the total momentum of both carts? And if we had done the lab perfectly, in real life, nothing's perfect, but if we had done it perfectly, every single time, the momentum of the first cart would have matched the momentum of the second cart. All right? And once again, that's called the law of conservation of momentum. Now, you guys have studied a lot of conservation laws. Can you throw out a few from chemistry or physical science or junior high science? So Cindy, can you think of one conservation law that you studied? The law of conservation of blank. I'm sorry, Cindy, what did you say? Mm. So Cindy, what science class were you in last year?
I don't even remember.
Were you in chemistry?
Yeah.
Okay. So if you were in chemistry last year, do you remember studying like balancing equations? Did you do that?
To be honest, I kind of forgot everything.
Oh, all right. No, that's fine. So someone's helping you out right now in the chat. So the reason I brought up balancing equations is because all of the mass, all of the matter that you put into a reaction has to be accounted for at the end of the reaction. So you studied the law of conservation of mass. And basically what the law of conservation of mass said is that all of the mass before a reaction happens is going to be equal to all of the mass after the reaction happens. There's the law of conservation of energy, and it says that energy, cannot be created or destroyed, right? So all of the energy that you have at the beginning of an event is going to be equal to all the energy at the end of the event. Yep, and a second person chimed in. So the law of conservation of mass says mass cannot be created or destroyed, right, in a chemical reaction. The law of conservation of matter or momentum, you guys, it's basically the same thing, all right? So the first thing to know is that in a closed system, the total momentum is fixed. And what that means is that if there's no outside inputs, all right, the total momentum stays the same. The momentum that you start with will be the momentum that you end with. So in our lab, we started with 0 momentum. We didn't have any outside forces, all right? When Mr. Hammond pushed that button, what happened was there was an inside force of the two carts pushing each other apart. All right. So the forces came from within the carts. So if it started with zero momentum, it has to end with zero momentum. If it started with, 100 kilogram meters per second of momentum, it has to end with that. So in a closed system, total momentum is always the same. It stays the same. Now the other thing is that momentum can be transferred from one object to another. So in our experiment, we started with zero and we ended with zero. But we could have, say, an object hit another object and transfer its momentum into the other object. If you've ever seen anybody play pool, or if you have played pool, that's what happens, right? You transfer momentum from one pool ball into the other. So you hit the cue ball hits another ball, and the momentum from the cue ball goes into that ball and makes it move. So you can transfer momentum between objects. But the total momentum is always going to be the same. So the total momentum before your collision or before an explosion always equals the total momentum after the collision or the explosion. And I'll share these slides with you guys just like I always do. All right, so what we did in our lab is we created an explosion. All right, we had two objects and then they exploded apart from each other. All right, now in these explosion problems, it doesn't have to be like a bomb going off, right? But in these explosion problems, the total momentum before the explosion happens will be zero. Just like with those two carts, they were sitting still, they weren't moving. After the explosion, the total momentum has to stay zero. In your cart lab, and if you look at your data and you look at that table, the momentum of the first cart and the momentum of the second cart, they're almost always exactly the same. All right? It's the only way that we can make the total momentum zero, because remember, velocity is a vector and momentum is a vector. So momentum has direction. If one direction is positive, the other direction has to be negative. So if one cart has plus 10 kilogram meters per second of momentum, the other cart would have minus 10 kilogram meters per second of momentum. So it'll always equal zero. We have this video here that I'll show you. So we have these really super old cannons, all right? Now, these cannons, they're going to explode cannonballs. So they're going to push them out of the cannon. Cannonballs, you guys, are really, they're pretty heavy. Okay, they're pretty big projectiles. And so when I hit play, the cannonball is going to get positive momentum. So it's going to go what we'll call in the forward direction. All right. Now it'll have a certain amount of momentum going forward. The cannon has to have the exact same amount of momentum. And what direction will it move? If the cannonball goes forward, the cannon has to move how? It has to move backwards. That's right. So if the cannon goes forward, the cannonball goes forward, the cannon has to go backwards. So let's hit the play button and we'll see if our prediction was right. Did you see what happened? So the cannonball, here I'll replay that because it doesn't take very long. So the cannonball is going to move forwards and the cannon moves backwards, and it moves backwards at a pretty good rate. So you see that you wouldn't stand right behind the cannon because you could get hurt if you did that, right? And the reason that happens, you guys, is it's the laws of physics. The total momentum was zero before that cannon exploded. The total momentum has to stay zero after that cannon explodes. Instead of using a cannon, let's make it a gun. All right. So let's say that I have a gun. Oops. So let's say that I have a gun. All right. There's my trigger. So I have a gun and I have a bullet. All right. The bullet is going to go in one direction. That's like the cannonball. The gun is going to go in the opposite direction. Now, just so you guys know, this backwards direction, we call that recoil velocity. So the bullet gets pushed forward, and then the gun is going to get pushed backwards. And this is true of a cannon and a cannonball. It's true of a rifle and a bullet. You know, anything shooting a projectile, the projectile is going to go forward, and the thing shooting it will go backwards. All right. So the momentum of the gun is going to have to equal the momentum of the bullet. They'll just always be in opposite directions. So one would be in the positive direction, one would be in the negative. So the mass of the gun times the velocity of the gun is going to equal the mass of the bullet times the velocity of the bullet. Now, I'm going to ask you a question. This always kind of scares me a little bit when I ask it. I don't know why, but I'm sure many of you have held a gun before, all right? And probably a lot of you have held a handgun. Some of you may have held a long gun like a rifle, but many of you may have held a handgun. Now, for anybody who has held one, okay, I have, it's legal, right? So for anybody who's held one, what was the very first thing that came into your head about the gun itself? Not about being scared or any of that stuff, right? Which you may have been. But what about the gun itself? Every time that I ask someone this question, I always get the same answer. The very first time they held a gun, they were surprised at something. Can someone type it in there? Yeah, they're really heavy, right? So there's a reason why guns are heavy. And here's the reason, you guys. I want you to think about this. This bullet, okay? This bullet is going to be going really, really fast, all right? It's going to have a super, super huge velocity. So I'm going to have the velocity of the bullet. It's going to be really big. Now, the mass of the bullet is pretty small, okay? But this bullet can go, up to 200 miles per hour out of this gun, all right? Now, I definitely don't want the gun coming back at me at 200 miles per hour, right? I know the momentum has to be the same. So if in order for me to make this velocity of the gun smaller, as small as possible, what I have to do, oops, what is going on here? I just lost my pen here. Hold on. So in order to make the velocity of this gun as small as possible, you guys, I have to make the mass of the gun really big. So if I have a really big mass, I could have a small velocity. Over here, the mass of the bullet's really small. I could have a big velocity. All right? But the momentums have to be the same. So in order for me to make this recoil velocity as small as possible, the mass of the gun has to be as big as possible. All right? Now, I can never, ever fire a gun without it coming back at me, right? No matter how heavy the gun is. So if you fire a gun, especially a handgun, you need specialized training to have it. And part of that training involves like the proper use of it. You can't hold a gun. Like if you can see my picture, you can't hold a gun like this, all right? You can, but you will be completely inaccurate with it, and you really only get off one shot. Because if you hold a gun away from your body with one hand, the recoil is going to push it back, and if you fire a second bullet, it's going to go in a completely different spot than where you meant it to go, right? When you hold a handgun, you have to hold it with both hands, right? You have to lock your arms, and that's the only way you can control the recoil. So that if you have to shoot the gun again, the second bullet goes in roughly the same spot. All right. Now, you guys, long guns, usually rifles, or let's think about a shotgun if you've ever seen one of those. Shotguns are used for hunting like ducks. And the reason that you would use a shotgun is shot is like a whole bunch of little pellets. All right. And those pellets spread out so that when the duck is flying, it's like it's quote unquote scatter shot. The duck will fly into the path of those pellets, and you have a better chance of shooting it. Okay. Now, because you have so many of those pellets packed into one shot, the bullets in a shotgun are really heavy compared to the bullets in a handgun. So shotguns have to be even more massive, and not only that, even if they are more massive, the recoil is pretty big. So you don't hold a shotgun out once again with one arm. I know you might see that in the movies, right? But that doesn't work. You put a shotgun, you actually rest it against your shoulder, and you hold it with two hands. All right, and you kind of lean into it a little bit. Otherwise, it could hurt you. My son, he's younger, and at scout camp, he fired a shotgun for the first time. Even though he was told to put it against his shoulder, he held it off his shoulder because he was a little bit afraid, and he had a huge bruise. Right? Why? Because this recoil velocity is pretty big. All right. So in any of these situations, the momentum of the bullet is going to be equal to the momentum of the gun. So if we go back to our lab, you could have called the gun the cart with the piston, and the bullet could have been the cart that was getting pushed, right? The momentum of one cart has to equal the momentum of the other cart. The momentum of this object has to equal the momentum of this object. They're just in equal and opposite directions. So let's look at how this works in a problem. Let's do a problem. So I have a cannon. It's a fairly small cannon, 5.5 kilograms. That would be like 11 pounds, you guys. It's loaded with a 52.7 gram cannonball. So here we go. I'm going to have the mass of the cannon is going to be equal to 5.5 kilograms. Okay. And the mass of my cannonball, we'll call it CB, is going to be equal to 52.7 grams. Now to get that in kilograms, we would divide it by 1,000. So it's going to be 0.0527 kilograms. Okay. So the cannon is ignited and it launches the ball forward. So the ball is going to go forward. The cannon is going to go backwards. Okay. The cannonball has a forward velocity of 75 meters per second. I want to know, what is the backwards velocity of that cannon? So in my picture here, the mass of the cannon, the velocity of the cannon, they're both going to be going backwards, and then the cannonball is going to be going forwards. All right, and this m times v, the mass times velocity for the cannon, has to equal the mass times the velocity for the cannonball. So I would have the mass of the cannon times velocity of the cannon. That has to equal the mass of the cannonball times the velocity of the cannonball. So I have 5.5 kilograms times the velocity of the cannon equals 0.0527 kilograms times 75. That's just supposed to be a parenthesis. So this, if I do my arithmetic, this is 5.5 times v, and that's equal to 0.0527 times 75. Does anybody know what that is? I got it to be 3.95. Now to get rid of this 5.5, what am I going to do? Can someone tell me? They're being multiplied, so I have to do what? I have to divide, right? So I'm going to divide both sides by 5.5 kilograms. And I end up with 3.95 divided by 5.5. I get that to be 0.72 meters per second. So the cannonball was... I'm sorry, what was that?
If you could just move it up a little bit.
Oh, can I move it up? Yeah, I'm sorry about that, you guys. This is all happening because it's hard for me to write. On these screens here. Oops. Is that better? And what I could do is I can type this out so it'll make it easier to see. Okay, so can I go to the next slide? Can I get a thumbs up or an okay in the chat? Okay. So let's look at this problem. This is another explosion problem. So I have two ice skaters. I have a male ice skater facing a 42.8 kilogram female ice skater. So I'm going to draw, not the best artist on the planet, but here's my two ice skaters. One of them has long crazy hair. I don't know which. We'll make it the girl. So her mass is 42.8 kilograms. Okay. Now they start out at rest on the ice, and then they push off each other. So you may have seen this move if you watch like the Winter Olympics or you're into ice skating. So when they push off each other, she's going to go in this direction. He's going to go in this direction. Now they'll have the same momentum. All right. It says that the male skater moves at a velocity of 2.14. Oops. 2.14 meters per second. And the female skater moves at a velocity of 3.11 meters per second. Okay. I want to know what is the mass of the male skater. So right now, you guys, I could tell you that the male skater has to have a mass bigger than 42.8 because his velocity is less. If the velocity is smaller, the mass has to be bigger. If the velocity is bigger, the mass has to be smaller. Now, you saw this yesterday in your lab. So when Mr. Hammond started piling heavy weights into one of the carts, that cart, the cart with the heavy weight, always had the smaller velocity, and the cart with the lighter weight always had the bigger velocity. All right? Just like our gun and our bullet, or our female skater and our male skater. So I know that the mass of the boy, we'll just call him the mass of the boy times the velocity of the boy, has to be equal to the mass of the girl times the velocity of the girl. So I don't know his mass, but I do know his velocity is 2.14. Okay. And then the girl's mass is 42.8. And her velocity is 3.11 meters per second. So I got to plug that in my calculator. 42.8 times 3.11. So I got 133.1. You can check my math. And then I have to get rid of this 2.14, right? If I want to get rid of that 2.14, I'm going to divide both sides by 2.14. Sorry, I got all the way to the bottom again. And those are going to cancel out. And so that means the mass of the boy is going to equal 133.1 divided by 2.14. Oops. I punched the wrong thing in my calculator. And I get his mass to be 62.2 kilograms. And once again, you guys can check my math. And I'll move all of this stuff up on the page. Okay. So any questions about that problem? No questions so far. All right. That means I'm moving on, right, to the next one. Okay. So, this hopefully should look familiar, right? I have two carts, and they're going to push away from each other. So one has the piston in it, the other one doesn't. So I have cart number 1, and cart number 1 has a mass of 1.5 kilograms. Carts have to have wheels, right? And then I have cart number 2, and cart number 2 has a mass of 2.5 kilograms. Now, cart number 1, it says has a velocity of 5 meters per second. I want to know what is going to be the velocity of cart number 2. So remember, m times v here, that has to equal m times v here. So we could call this like m1v1 for cart 1. We could call it m2v2 for cart 2. But this m and v has to equal this m and v for these explosion problems. So I'll have 1.5 times 5 equals 2.5 times v. Now I could tell you right now that this velocity has to be smaller because the mass of this cart is bigger than this one. So 1.5 times 5, that's 7.5. And you guys probably don't even have to use your calculator for this. We want to get rid of that 2.5. So we divide because it was being multiplied. Now these 2.5s, they're going to cancel. So the velocity will end up being 3 meters per second. So once again, the mass was bigger, so the velocity has to be smaller. So is everyone good so far on these explosion problems? Yes, good. All right. So there's a problem set, you guys, for explosion problems. You can do those. Now we have one more type of problem that we need to talk about, and that's what happens when two objects collide into each other. So just like before, the total momentum before the collision is going to equal the total momentum after the collision. Now with the explosion problems, the total momentum before was 0. So after the collision, it still had to be 0, right? So this really isn't different, except in these collisions, the momentum before and the momentum after won't be 0. Unless they were heading straight at each other at the same speed. So let's think about something for a second. I have a school bus, and it's moving down the road. It's going 25 miles per hour. It hits a bug on the windshield, and the bug splatters all over. You guys have probably seen this on your car, especially when you're driving like down south. You're driving towards Texas, through all those cornfields, lots of bugs. All right. So I want to know which object experiences the greatest force of impact, the bug or the windshield. So I need everyone right now, type your answer in the chat box. Don't be influenced by other people. So I have 3 people that did it so far. So either everybody has a really good physics teacher, or you're really smart, or you kind of all followed each other. So the force of impact, you guys, is the same, right? It has to be the same because Newton's third law. For every action force, there's an equal and opposite reaction force. I like Caitlin's answer. So the bug, the force on the bug is going to be the exact same as the force on the windshield. Remember, it's just that the windshield can withstand a bigger force and the bug can't. Okay. Now, I thought I took this one out. I'm sorry. We haven't talked about impulse yet, so that's we can't answer that one. We're going to do that next. But which would experience the greater momentum change? Now, if total momentum of a system stays the same, then the momentum change of the bug and the momentum change of the car should be the same. Right? This is because of the law of conservation of momentum. So this was Newton's third law up here, right? And this is conservation of momentum right here. Now, which object experiences the bigger acceleration? Well, that's going to be the bug, right? Because remember, F equals ma. That's a Newton's second law. The bug has a really, really little mass, so it'll have a big acceleration. The car has a really big mass, so it'll have a small acceleration because the forces will be the same. Okay, so let's look at a problem. This is probably all we're going to be able to get through, and then I'll cut you guys loose to work on your homework. All right. So in this problem, I have a 3,000 kilogram truck. It's moving at a velocity of 10 meters per second. And then I have a poor car here that's parked on the street. It's 1,000 kilograms. And when the truck hits the car starts moving at 15 meters per second. Now, we're going to assume that momentum is conserved because that's the law of conservation of momentum. I want to know what's the velocity of the truck. Okay? So to do this problem, you guys, we have to think about the before and the after. So before anything happens, that total momentum, the total momentum here, before anything happens, has to equal the total momentum over here after everything happens. So I like to draw little pictures. I always draw little pictures out when I do these problems. It just helps me out. Might help you guys out too. So I have the mass of the truck. The mass of the truck is going to be 3,000 kilograms. And it's not going to change before or after the collision. sometimes the mass can actually change. If you've ever been in a bad accident, you know pieces of your car fall off. It's craziness. But so anyway, so I have a 3,000 kilogram truck and it's moving at a velocity of 10 meters per second. Now it is going to hit a car. The car starts with a mass of 1,000 kilograms. Now the starting speed of the car is 0 because it says in the problem right here that it's a parked car, right? So I have the 3,000 kilogram truck. It's moving at 10 meters per second. It's heading towards this car that's parked. Car has a mass of 1,000. Okay. Now, so the total momentum here before it hits, that would be 3,000 times 10 plus 1,000 times 0. Now, all of that momentum is going to have to equal the momentum afterwards. So we know the mass of the car, once again, it didn't change, still 1,000. Okay. And it says that the impact causes the car to be set in motion at 15 meters per second. So the new velocity of this car is going to be 15 meters per second. Determine the velocity of the truck. So this is what I'm trying to find out. So this truck, when it hit the car, it gave it some of its momentum. So the truck here was moving, car wasn't. Now the truck hits it, and it gives up some of its momentum to the car. If it gives up some of its momentum, it's going to lose some of its velocity. So it was going 10, it'll be going slower after it hits it. And why? Because the car gained some of the momentum from the truck. So we'll do this problem. The momentum of the truck is going to be 3,000 times 10. The momentum of the car before it hits is going to be 1,000 times 0. Now remember, that has to equal the momentum afterwards, which is 3,000 times v plus 1,000 times 15. So 3,000 times 10, that's 30,000. 1,000 times 0 is 0. 3,000 times v, that would be 3,000 v. And 1,000 times 15, that will be 15,000. Now, I got to get v by itself, so I have to move this 15,000 over to this side. It's being added, so what will I do? Who can tell me? Yep, I will subtract it. So I'll subtract 15,000 from that side, 15,000 from this side. And here it's going to cancel, right? So then that leaves me with, and 30,000 plus 0 is just 30,000, right? So 30,000 minus 15,000, that'll be 15,000 equals 3,000 times v. Now we've done this a few times. I want to get rid of this 3,000. So I'm going to divide both sides by 3,000. And once again, on the right-hand side, the 3,000 is going to cancel, right? And 15,000 divided by 3,000, I'm just going to write the answer here. The velocity of the truck is going to be 5 meters per second. So in this problem, the truck lost half of its momentum, lost half of its velocity, and it gave half of its momentum to the car. Now, because this truck was so big, right, when it transferred its momentum, the car actually started moving faster than the truck was originally, right? This is why accidents involving really big vehicles can be very dangerous, especially for the people in the smaller vehicle. So I'm sure you guys have seen these tiny little smart cars driving around. If you're in one of those little cars and you get hit by a really big SUV, that can be very dangerous, right? And it can be very dangerous because of this momentum transfer. So this car went from 0 to 15 meters per second, and that happens very, very quickly, you guys, right? So if the time is really short, that means the acceleration is really big. And if the acceleration is really big, we just did Newton's laws, right? If the acceleration is big, that means the force will be big. So the people in that smart car will feel a really big force if they get hit by a big vehicle. It would be much better for them to get hit by another smart car, right? Or if, let's say, if you were in a big vehicle and you got hit by a smart car, you know, you would feel much safer because you would have bigger mass, meaning smaller velocity. Smaller velocity change means smaller acceleration, smaller force. So I hope that makes sense, right? And it's probably something you knew, you just actually didn't realize you knew it, probably, or you didn't know the reason behind it, right?